Hi everybody, my name's Tony Abbey, and I'd like to just introduce myself. I produce a lot of videos on FE analysis. I have a website which is devoted to resource and web FE analysis. I also post a lot on both YouTube and LinkedIn. So I recently came across a video by a gentleman who's with me today, Lukasz. If you'd like to say hi, Lukasz. Hi, Lukasz. And
Hi.
Lukasz Skotny posted a very interesting video on his website, and I saw it and I reposted it on LinkedIn, and we had a lot of interest. There was a lot of hits on that, a lot of comments and so on. So we thought we'd get together and chat a little bit more about this phenomena of Snapthrough in particularly. So we decided to record it and present it here. So Lukasz, I watched your video on Snapthrough. I got a couple of questions, but I wonder if you could first summarize Snapthrough to those who are new to the idea.
Sure. So, hi, my name is Lukasz. I run a blog on enterfea.com, and I've been researching Snapthrough because I did a PhD on shell stability, so it's a problem close to my heart. And I also really like it because it gives you a chance to showcase your skill in some sense in FEA, because it's not a simple problem to solve. And it kind of shows that you know what you're doing when you can do it. So it's like, I really remember the first time I solved a problem like that, and I was like super happy. So it brings back good memories, I guess. So basically a snap-through problem is a situation when you have a stable system of some sort, and then you load it and it's stable for a while, and then it will reach a second stable state that looks usually pretty different than the first one. And the transition between those states is actually pretty funky, and it's very interesting to observe it, but also it's pretty difficult to check that in a test as well. So there are many approaches to how you can try to verify the capacity due to this phenomenon.
Okay, thanks, Lukasz. I ran a similar problem, and to you, and in fact, people can see both our animations and so on. They're appearing down in the kind of the graphics areas we're talking. Now we both used a variety of loading conditions, and this is again part of what the classic benchmark approach will take. We can apply a force, and we can then see how that force will affect the snap through, how it achieves the snap through. Then we can also apply a displacement controlled approach, and again we'll see from the videos that we're getting different kind of responses. Basically, a displacement based approach is able to control the solution a lot further. And then finally there's a technique, there's a bunch of different techniques called the arc length techniques, which search through and find, again on the animation we'll see below, a little image of what we call a snap back, where it actually can recover and kind of go in a negative displacement sense. So these are very much kind of theoretical type solutions. This is what comes out the FE analysis. 3 different forms of this analysis. Lukasz, I wondered if you'd like to comment on how this relates to the real world, because I know you do physical testing at your university. How does a theory relate across to how you would set it up, say, physically?
Well, in all honesty, snap-through is pretty complex to model in a laboratory setting. Basically, it's impossible, as far as I know, to have an arc length approach to apply load in your test setup. Like, this is undoable. Like, mathematically speaking, it's a very sound method, but in real life, there are no gear that does that. So what you are stuck with is either applying a constant, like increasing load, or applying increasing deformation. Increasing load would be pretty difficult, but you can imagine that you can have a model like you can see here, and I will hang a very big container below it and simply add sand to it. And the more sand I add, the bigger load gets, so it pulls downward. And this is like a force control. I control how much force I am applying. And what would happen there, I will come to a place where I reach the capacity of the system, and then it's a good idea not to stand nearby because it would snap, and like it most likely makes a lot of noise. So that's one setup, and it works basically to the point of collapse. The second approach that usually is used is to control displacement, mostly because it's safer in a sense. Because even if something is collapsing, you're kind of keeping it at place because you're controlling how it displays. So imagine I have a hydraulic press, for instance, and I could put it on top and simply extend the tube of the press. And I can say in which speed this tube is extending. Of course, by the extension, it applies a load to the structure I'm analyzing, because this allows it to extend more because the structure had to deform. But in a sense, I am applying a deformation because this is what I do, this is what I measure as well. So when the thing starts to collapse, to some point I can control how it is collapsing, but Snapthrough, like in shell stability problems, most of them, this would be sufficient, but Snapthrough also is associated with snapback, and that's another problem. So I would say that in general, when you do FEA, you can try to capture each and every equilibrium state as the model snaps from one stable state to another. But in reality, it's not so simple because of things you miss when you actually mathematically analyze each stable state on a path.
Okay, so it's kind of summarizing then, force controlled, you just have a monotonically increasing force, and eventually you're just going to rupture the component, or it's going to collapse. But with displacement controlled, you can actually have a backing off of the load, can't you? So your load cell could be seeing a drop of load. So you can literally unload when you're displacement controlled. And therefore it's a more controllable state. But as you're saying, where does arc length leave us? It's a mathematical concept. I guess somebody could figure out some experimental or test approach, which would be an analog, but it would be very difficult to do that. You made the comment that modeling the physics is very, very tough. And on the LinkedIn posting that we did, there were a couple of comments which were really interesting. And one of them came back to say, well, in fact, it's a dynamic event, which is absolutely true. It all happens very rapidly in this form of instability. Others can happen more slowly, but this one happens very fast. So the transition between what you're describing as the initial stable state and the final stable state happens, really quickly. And it is a dynamic event. So being dynamics, what we're missing out is inertia. We're also missing out damping. Damping's hardly going to matter because it's happening so quickly, but the inertia term, as commented on the LinkedIn post, tends to smooth out that transition. And I think also it's probably easier to get convergence in a nonlinear analysis, in my experience, if you've got inertia terms there. If you use a nonlinear dynamic term, inertia term, that almost acts like a memory. It remembers where you were at the previous step. The inertia term is building up. Whereas if we just do a static equilibrium, it's like, what am I doing? I'm starting from scratch at each step. So having said that, it's a dynamic event. Do you think it matters the fact that we're using, and pseudostatic is like, as you emphasize, it's equilibrium at each stage, static equilibrium. Now we're saying it's really a dynamic event. Do you think it matters that we miss out dynamics in this particular case?
Well, I would say it depends on what you're after. But in like a design that I mostly do, I would say it will come in handy to have a dynamic analysis if you are very interested in what really happens during the snap-through. But usually the point is to realize at which load the snap-through happens. So as long as you want to design a safe structure, you like knowing that snap-through happens at this level of load, it's a sufficient information. Like how exactly this happens rarely is of interest, even though sure, it feels nice to be able to do such an analysis without a doubt. But practically speaking, I would say that as long as you can say the process starts at this particular point, I am safe to say that this is what counts. And static analysis in this particular case is easily sufficient to do something like this. So I would say that as long as you are certain that you can simplify something, simplifying it actually makes tremendous sense because, it's less computing involved and all that. So you actually can save a lot of time by analyzing something with a simpler approach that otherwise you would have to develop into sometimes incredibly complex problems. So sure, like I can imagine instances where dynamics like would play such a significant role that you can omit it. But in most practical applications, I can easily imagine that simplification is a way to go. Okay.
Yeah, and I think that's a good general message, isn't it? I think we've talked about that before. We've talked about that offline. We're trying to match the physics of the situation, but from a simulation point of view, we're trying to match it as simplistically as we possibly can. We don't want to miss out important physics, but we don't want to get too complicated. And I think your analogy there, or your summary, is very good. What are we interested in? That snap-through loading. So again, we had a correspondent on the posting who was actually, I think, looking at snap-through as a way of designing switches. So you press some kind of flexible switch, it snaps through, changes state, and so on, and that's what he's interested in. So I imagine, exactly as you say, that applied force, where does this occur, is critical. And then probably also, what is the final stable configuration? What happens in between? In this particular case, perhaps not, as you say, not very important. The only thing is we've got to be careful that we don't, in our simulation, we don't miss some other form of non-linearity that might have occurred, like if it went plastic or something during the snap-through, that would be an issue. But apart from that, we can just assume that, as you say, that our simplification works. I even go further, and I've often got into trouble with people. I say, well, if we can avoid nonlinear, then we avoid nonlinear. And if our physics can be modeled in a linear way, then why go to the risk in many ways, the complication of nonlinear analysis? Would you kind of agree that you're an expert on linear analysis, but perhaps do you have the same kind of approach? If you can avoid my area of expertise, then avoid it, which seems like a strange thing to say.
I think that it actually helps. Like, I've learned that I trust linear analysis much more when I know how to perform nonlinear analysis, simply because I understand what I am missing and when. And sure, like going blindly into a linear mode all the time is always risky because you don't know what you're not taking into account. But if you know what you're doing and you understand the limitations of the approach, I would say that most of analysis, even nowadays, is still done in a linear way, and definitely it's a lot of merit goes with that. And like, even the costs of running a company are lower because you don't have to have the best software out there. Most of them can do linear analysis, for instance, and nonlinear is still something extra in many packages. So even that is a plus. But I would say, yeah, I completely agree. If you can be certain that avoiding something isn't going to cause any trouble, then avoiding nonlinear analysis, by all means. Like, I do it myself. So obviously this makes sense, sure. But you need to be able to detect whether or not you can get in trouble by simplifying something.
Yeah, and I think we've probably both had experiences in our career where I certainly missed nonlinear effects and subsequently included them and found that they significantly affected the response, the structure. So what we're saying is be aware of it, but then, and I think the point's a very interesting one. This is a benchmark. It's a classical benchmark. People love to stretch FEA codes against this. So the snapback issue in particular is a tough thing to find. So I think it's a stretching kind of benchmark to get down into the mathematics, show that you're really getting the correct solution. But in practice, in reality, that snapback area, which again we'll have some diagrams below to show that area, is probably just not important in real life. And I think that's the kind of judgment call we're making here. It's always a kind of a judgment call. Again, hopefully there'll be a lot of feedback and comments on that, on this post, on this video. It'd be great to hear people's views. I had an ex-colleague who swore blind, the whole world is nonlinear. Every analysis you do should be nonlinear. So but he ran the nonlinear group, so he would have that view. But again, it's
comes with the territory, I guess.
Yeah, and it's kind of nice. You got a PhD in this area, done a lot of research in this area, but again, you kind of feet are on the ground. You're saying, you know what, if we can avoid it from the point of view of the physics and the answers we're trying to get, accuracy and so on, then that's a good thing to do. Now, I did notice that when we're looking at the videos, your videos and my videos, for the displacement controlled situation, a loading form, we actually saw some asymmetry, which I thought was very interesting. Again, when I first came across this benchmark, I won't say how many years ago it was, but the benchmark, and it's still posed as a quarter symmetry problem, and it's usually like a 5x5 mesh with quarter symmetry, because believe it or not, everybody, going back 30 years when I first came across it, now I've said it, that's all you could handle. So if you try to do a full model with, you know, a 50x50 mesh, which would be nice, and I recommend people use that kind of fidelity these days, it would be unrunnable. So again, it's interesting. It is a benchmark, and it got locked into this idea. Two things I don't like about it: the symmetry, and we're applying a point force. And in my training, I was saying never apply a point force because you get another form of singularity. So we got locked into this benchmark syndrome. But my feeling is that in general, symmetry, use of symmetry in nonlinear analysis is potentially a very dangerous thing, and it shows up here. What are your comments on that, Lukasz?
Well, symmetry definitely can make a huge model much smaller if you can apply it. So clearly, from time to time, I'm using it simply because computing, like, even though 30 years ago I was most likely in a kindergarten.
Don't rub it in.
Like even now, like the computers got faster, but models also got bigger. So symmetry, like we try to analyze more and more accurate things. So symmetry definitely helps with getting those tasks smaller. However, I always avoid symmetry in places where I expect something will fail due to stability. Because I simply cannot, like, even if I have a symmetry of a model and symmetry of a load, I'm never sure if the buckling thing, like how it will buckle in reality, will be symmetric as well. And by applying symmetry, I'm actually assuming that it will, and it doesn't have to be. So clearly avoiding symmetry in places where you expect stability issues is a wise move. And again, it comes down to experience. You simply need to expect something. And then even if I assumed initially, oh, I will apply symmetry here, nothing will happen. And then in the end, I see a stability failure in that region. I will say, okay, I cannot use the symmetry there and start again, simply because assuming that stability failure will be symmetrical can be tricky. And of course, there can be a lot of examples when it actually will be. Sure, by all means, but it doesn't mean it will always be like that. And I'm not willing to make this call out of thin air, let's call it this way.
Because that instability mode is a fairly chaotic kind of mode, isn't it? And there's nothing in nature that says it should be symmetric or it should be asymmetric. It just depends on whatever very local effects could be occurring, or maybe boundary conditions effects. It's that search for instability is like a tiptoe path, isn't it? Anything can influence that instability.
Yeah.
And it might decide to go symmetric, it might decide to go non-symmetric or asymmetric. And it's very interesting. I think following the literature and working in the field over many years, and there was a lot of fuss going back a few years when it was realized a lot of the classical solutions made symmetric assumptions, and it was shown that these were actually invalid. And there was a bit of a kind of a turmoil in the research field and the research area at that time, as a lot of early assumptions and so on were overthrown. But I think that the message to people watching who are embarking on this first time is don't use symmetry, as you say, any form of instability. The same way we wouldn't use symmetry for normal modes analysis, because our mode shapes are going to be symmetric, non-symmetric. They're going to be all over the place, and we are forcing the issue if we just use symmetry models. So I thought it was an interesting little point that came up there. There's a lot in this, isn't there, Lukasz? There's all sorts of things that we could pick out. It's interesting in our particular case, the initial, I think for both our models, the initial stiffness is lower than the final stiffness, and you can see that by the slope of the curve, the slope of the initial curve, and then the final curve of the load versus extension. Sometimes it goes the other way around. The secondary position is more flexible than the initial condition, and so on. So it's a fascinating world to see what goes on here. I think I'm going to finish up with you're a practical guy. You've done practical kind of test work. My only practical application of Snapthrough, I got to admit, is again going back in the day when I was a kid. We used to get tin toys in our Christmas stockings, and they were like tin beetles and tin frogs, and you pick them up and you click them, and they exhibited the Snapthrough. They were very carefully tuned by the craftsman, so it's like a croak or some sort of noise like a cricket and so on. Have you ever come across that? You mentioned before you're a lot younger than me, but actually, did you come across that?
I think I have a pistol or something like that. That when you pull the trigger, it actually had a small arc inside, and it applied the force in a way that it made like a second mode buckling, and then it snapped through to the full arc and make a noise, so I could like shoot with the pistol. So I guess this is still like the cheapest way to make sound in toys. So I'm pretty certain that some point my kids will get Snapthrough toys as well. So who knows? Maybe we'll be able to make FEA tests of those.
That would be interesting, and that perhaps. That would be then the physics gets really interesting, doesn't it? Because if you're trying to get acoustics coming out of it as well, then we're into like multi-physics and so on. So we've taken our humble Snapthrough to something very, very advanced indeed. Well, I think it was great. It was great chatting to you, Lukasz, and I think hopefully we've raised a few points of interest to people watching. Again, would stress to anybody watching, please, feel free to jump in. Contradict, comment, things you think we might have said which are rubbish, wrong. Please feel free to kind of chip in with your own thoughts. So I think we'll wrap up. But I just leave you, Lukasz, if you just want to summarize again your website and where people can contact you.
Sure. So we will provide links down below to both of our websites, and also, if you're interested, I have a free course that introduces you to Nonlinear FEA, so you can take that as well. I think that will be fun. And if you're interested, you can just go to enterfea.com/blog, and I try to write from time to time about stuff I find interesting, so maybe you'll find something there that simply interests you as well.
Okay, thanks, Lukasz. And from my side, again, wherever we end up putting it, we'll find links to my stuff as well. Again, I have a website. I do Nonlinear e-learning training partnership with NAFEMS, and this crops up in that, and you'll find information on the resource site. So with that, I think we'll say cheerio. So thanks, Lukasz, and bye, everybody. Thanks for your
It was a pleasure, Tony. Bye.
Take care. Bye-bye.